Welcome to everything you need to know about lithium batteries. I'm your host, Marcel Stieber, Alpha India 6 Mike Sierra. First, a little bit about myself. I was licensed in 2008 as Kilo India 6 Quebec Delta Juliet. Got my master's in electrical engineering from Cal Poly San Luis Obispo in California. I'm heavily involved still with the amateur radio club at my university, with the Cupertino Aries as a repeater trustee, and with several other event and repeater groups in the area. In my day job, I design battery and charging systems for consumer electronics products, so I've been playing with batteries for a number of years now, especially in the last couple of years with a lot more lithium. So today's presentation will focus on three common battery types. We'll give a little bit of a background on lead-acid batteries, then talk about lithium batteries, and then the most interesting one for us amateur radio operators, the lithium iron phosphate batteries. We'll discuss kind of pros and cons of each different type of chemistry, common ways you can use them, and then show you a couple different projects and kind of battery pack applications for each of them. My slides are all available on my QRZ page and as part of this conference, so hopefully you'll enjoy those as well. So a brief introduction to batteries. Batteries are fundamentally an electrochemical energy storage system. So they're constructed in layers and have an anode, an electrolyte, and a cathode. If you look at the battery here on the right, you can see all of these little anodes and cathodes and each of these plates in here. So you have these layers of this battery. This is very similar to the original battery in 1800s made by Alessandro Volta, which was from the zinc and copper plates with brine-soaked paper between them. So you can see the copper and zinc plates in this battery, and then the paper between them with that electrolyte. That actually allows the ion transfer to happen, which allows your battery to either charge or discharge if it's a rechargeable battery. I also like to point out that the schematic symbol here on the bottom left, that's the schematic symbol for a battery, and you'll notice it is made of layers. So in this case, you have 4 layers for that battery symbol, which is very much from the original battery construction. So it's always a little piece of interesting history I like to share. One of the key things we'll need for today's presentation is what we call a nominal cell voltage. So all different types of cells and different battery chemistries have a different nominal cell voltage. So the standard alkaline battery, the carbon zinc battery that we're all used to, is kind of a 1.5 volt cell. And then nickel cadmium, which we're also very familiar with, is at 1.2 volts per cell, which is why it's commonly used as a replacement for alkaline batteries. But the slightly lower voltage does mean that some equipment isn't very happy with it. So like your HT, if you use 6 carbon zinc batteries at 1.5 volts, you'll get a very stronger voltage than at 1.2 volt nickel cadmium stacked together. So your radio might think the voltage is already too low. And then lead acid cell voltage, nominal cell voltage for lead acid batteries is 2.1. So we'll get to that a little bit later because everyone will say, Marcel, a 12 volt battery is actually lead acid, but the individual cell is only 2.1, and that's key. So to get these full battery voltages, we have to stack these cells together and get up to what we want to get to. So for a 12 volt system in amateur radio, it's actually a 13.8 volt nominal system. And typically the specifications for radios in this range are plus or minus 15%. So if you look at the data sheets for your common Yaesu, Kenwood, ICOM radios, mobile radios, or HF radios, they'll have a 13.8 volt nominal and then a plus or minus 15 volts, which is about 11.7 to 15.9 volts. So we'll use that throughout the talk as well. And then this photo on the right, this is a 9 volt battery. And yes, that's what a 9 volt battery looks like inside. And if you look very carefully, again, you'll see these plates inside, right? So these are your carbon and zinc plates inside this cell. So when we count them up, there are actually 6 of these plates in here, and 6 plates at 1.5 volts per cell gets you to 9 volts. So it's actually very common to see this, and it's a great way to kind of see how those batteries stack up together. Some 9 volt batteries will have quadruple A cells inside, so if you take them apart and you see something different, fear not. There are still 6 primary cells in series to get you 9 volts. Okay, let's start off with some lead acid batteries. So lead acid batteries are lead and acid, so they have pure lead and lead oxide as the anode and cathode, with sulfuric acid as the electrolyte to move the ions back and forth. They were invented in about 1859, so they've been around for over 100 years. And they have then 6 sets of plates to get to your 12 volt battery, right? So 2.1 volts per nominal cell. You stack 6 of them together and you get a 12.6 volt nominal battery. So here, this on the left is a cross-section of, I think, a motorcycle lead-acid battery, and you can see there are 6 chambers here, right? Each of those is a primary cell that gets you up to the 12 volts. Similarly, on the right, here's kind of a cutaway image, and you can see each of these chambers is then connected in series to the next set of plates, and then to the next set of plates, all the way to get 6 in series to get your 12.6 volts nominal. Lead-acid batteries are everywhere, but they have a number of drawbacks. The key one is that they're very, very sensitive to deep discharge. So they really aren't able to deliver the full rated capacity when you're using them for 12-volt radios. Typically, they're only rated for what's known as a 50% depth of discharge, which means you're only discharging half of their rated capacity. So if it's a 10 amp hour battery, you're actually only using about 5 amp hours of usable capacity before you start damaging the battery. So really, you don't want to run those to zero. At a 50% depth of discharge, you get less than about 500 cycles off of them, which for normal like backup battery use and stuff is not an issue, but in solar applications or any application where you're cycling the battery heavily, that can be a big problem. The next item that's also not great is they are heavy, right? They're called lead-acid batteries, and lead is notoriously heavy, so they have a low gravimetric energy density. That's the official term for it. Additionally, they have a 5-year shelf life, is pretty typical for SLA or sealed lead-acid batteries. This is the manufacturer's specification, so if you look at the data sheet, it will tell you 5 years is all you get. And be careful when you buy batteries, even from your local department store. Check the date code stamp on the battery and ask for a discount if it's already been sitting on the shelf for 2 years. I've found that before, and ask for a 40% discount because it's already 40% used up. But they are cheap and readily available and everywhere. As a result, they're really easy to connect to things, right? You can just hook up power poles directly to your radios. You can use standard chargers and interface boxes for any automotive battery chargers or isolating switches or regulators or anything. There's a lot in the amateur radio world that interfaces. PowerWorks and West Mountain Radio and another of other manufacturers make a lot of these. So lots of different applications. Very commonly used for emergency power. The photo here in the bottom middle, that's actually at one of the repeaters that I run, and it still has a lead-acid battery just hooked up. Very straightforward. I do want to point out one thing. The common images that you'll see for hooking up a lead-acid battery here to your radio with something like the Super Power Gate from West Mountain Radio, they'll just hook them up directly. The one key thing that they're missing in most of these block diagrams is an undervoltage lockout or a low voltage disconnect. This is really critical for lead-acid batteries because, like we said, they're sensitive to deep discharge, and if you over-discharge them, they will get damaged irreparably. Similarly to your car, if you leave the lights on in your car and it drains the battery completely, you pretty much need to replace the battery. It won't recover very well. It might still be able to start the car a couple times, but you'll definitely want to think about replacing that sooner than later. So West Mountain Radio sells a nice PowerGuard Plus, so a nice unit, nicely boxed up, or you can go onto eBay and get latching relays with configurable disconnect and reconnect ones for the right amperage that you want, and those work great. I've had good luck with those sorts of modules. And here's one of those batteries put into service. So this is a 108 amp hour battery put in with the power supply here and the Power Gate PG40S, and then there's a little low voltage disconnect down here. As you see, this 108 amp hour setup with the battery backup is 74 pounds. So it's quite heavy. That's definitely something to consider when you're working with lead-acid batteries. All right, on to the meat of the presentation, lithium-ion batteries. Lithium-ion batteries come around in about the 1970s, so this is about 90 years later. They came out with lithium-ion batteries. So this is same kind of anode-cathode electrolyte setup, but they use what's known as a jelly roll construction. So this gets you a much larger surface area. This photo here on the bottom left is actually one of these batteries unrolled completely. So they're actually rolled up inside these cylindrical cells and completely unrolled. That's what it looks like. So you have your anode, your cathode, you have electrolyte in there, and then there's a separator as well. Since it's rolled on top of itself, you need to have some sort of insulator between those to make sure that it doesn't short. Because of this construction and of the chemistry used, you can get a much higher specific energy when compared to lead acid. So in kilojoules per kilogram, you can get 460 versus 140, and that's a really big gain. This is why lithium-ion batteries are so prevalent in consumer electronics today. So again, our nominal cell voltage is important here. It's 3.6 volts is kind of typical. 3.6 or 3.7 is kind of typical for normal chemistries for lithium ion, with a voltage range for that cell anywhere from 3 to 4.2 volts typical. But I have to say there are a whole bunch of different types of lithium ion batteries. These are just a few of the common ones: LCO, NMC, LMO, and LFP. Those are just three-letter acronyms for all the different chemicals that are used to make these different chemistries, right? And they'll optimize them for different things. So like an NMC battery, nickel manganese cobalt, or LFP, lithium ferrophosphate, that's the lithium iron phosphate battery. Those will have different optimizations either for cycle life or for higher capacity or for higher ampacity, so the ability to deliver a higher current. So it really depends on application and what they're used for. You'll typically have two different form factors. They're pouch cells. That's the photo on the bottom left. Those are typically in phones, tablets, handheld transceivers, RC planes, quadcopters, anything like that. They don't have a hard shell around them, so they're very delicate. They have to be packaged carefully, but they're very flexible. You can change the shape and size and get them custom made for whatever size is needed for different manufacturing processes. Cylindrical cells are the very common ones that most people have heard of, the common size being the 18650 cell that I'm showing here in the middle. This is 18 millimeters diameter and 65 millimeters long, so it's a size designation for that form factor. Similarly, 21700 has been made pretty well known now by Tesla because they've started making the larger cell, which gets you a little bit better energy packaging capability because you can fit more inside those cells. These are commonly used in older laptops and electric vehicles, and mostly tool batteries is really the common one. So if you take apart one of these Ryobi or DeWalt battery packs, you'll find the cells inside are typically cylindrical cells that are rated for very high discharge, so very high ampacity that they can put out 10, 20, or 30 amps per cell sometimes even, which is pretty impressive. I should note that a lot of electric vehicles these days are starting to use pouch cells or prismatic cells or other format as well. So cylindrical cells are not necessarily what all of the EVs use. It's quite mixed these days. The key thing about lithium-ion integration is they are extremely sensitive to overvoltage and overcurrent events that cause thermal runaway, which is the nice way of saying that a battery decided to spontaneously disassemble itself. So as a result, you need to have protection circuits built in. This is absolutely critical, and the battery's chargers need millivolt accuracy. For a lithium-ion battery, a plus or minus 30 millivolts can make the difference of thermal runaway or being in safe operating range. So it's really critical that these systems are set up correctly, that they're configured for the right chemistry, that the chargers are very well done. The famous hoverboard incident is from chargers that were not properly managing their output voltage and caused batteries to go over voltage and thereby spontaneously disassemble themselves. So for multi-cell packs, you really need some form of battery management system with the minimum protections of OVP or over voltage protection, OCP or over current protection, and OTP or over temperature protection. So that's the bare minimum. But really you need under voltage lockout or low voltage disconnect, cell balancing, which we'll talk about in just a moment, and fuel gauging is a really nice to have. That gives you like the percent capacity remaining for a battery. Really, really useful. So this bottom left photo, this shows you 4 cells in series here. So if we're using 4 individual cells, this is the battery management system, the BMS for it. And the key thing to notice is there's this voltage tap between each set of cells. So what that means is this chip can monitor an individual cell voltage with high precision, right? So every single individual cell can be measured to millivolt accuracy. So as you're charging this cell, this pack, if any one of these cells goes above or below some threshold, you can disconnect the whole pack and safely protect the system. And that's absolutely critical. So that's really key to having a safe system, is having a good, well-configured battery management system. So the bad thing about lithium ion is 3.6 volts doesn't work very well for 13.8 volts, so that's a challenge. But it can be a very good fit for non-standard radios like HTs, where they can purpose design the batteries for that radio or vice versa. Um, and their cycle life is hit and miss. Kind of depends on what kind of cell you're buying and what sort of usage you're doing. Typically, 3 to 500 cycles down to 70% remaining capacity is pretty typical. But there are chemistries that do better and worse. Um, and they're used everywhere, so the cost has really come down quite a ways for these packs. The one thing I want to touch on is lithium ion system integration. This is a thing that we call the series and parallel configurations, and it's an S and P terminology for talking about how packs are built. So on the left here, this would be an example of a pack with 3 cells in parallel and 1 in series. So it's a 1S3P pack. This would be if the bottoms negatives were all shorted and the positives were all shorted, so this would just be a 3.6 volt pack. And then right here you have a 3S2P, right? It's 3 in series and 2 in parallel. So you have 3 times the voltage of an individual cell and twice the capacity of an individual cell. So if these are 2000 milliamp hour capacity cells, this pack would be 4000 milliamp hours. So that's really helpful to know that. So when we take these configurations and we multiply them into either a 3, a 4, or a 5 series pack, you can see that it's not a good match for lead acid. I'll actually go to this slide and show you kind of how these fit in. So on the left here, this is the mobile radio range. That's 11.7 to 15.9, that 13.8 plus or minus 15%. Here's where lead acid batteries sit, kind of on the lower end and drooping down. So there's that bottom 50% that we really shouldn't be touching. So for a 3S lithium ion, you can see it's not a great match. It's pretty low and drops down. A 4S is actually not bad, but there's a little bit that you lose up here at the top. So you can actually take a 4S battery pack and hook it up directly to your radios as long as you have not charged it fully. So if you reduce the top of charge to only, let's say, 3.95 volts per cell, you could actually plug it in directly to your radio, but you'd lose anywhere from 10 to 20% capacity, depending on what it is. But that could be good instead of using a buck or a boost converter, which has noise and efficiency concerns. So it's something to consider. And then for a 5S pack or anything more than 5S, 5 or 7S, you'll see that the voltage is obviously just higher, so you'd need to use some sort of buck converter. So I did exactly that. I took a DIY Powerwall kit and added a buck converter to it. This was actually designed by Justin Garcia and Jehu Garcia and my old roommate Justin Kenny, KJ6KST. He actually helped with the layout for this design. And I built a 7S10P battery pack with a built-in battery management system for about a 26 amp hour capacity pack. Put a 30 amp buck converter on it, and it works great. So here's the block diagram. I won't go into much detail, but pretty much you have your battery bank with the battery management system, absolutely critical, and then a buck converter attached to the outside. And with that buck converter on the outside, we have a 30 amp regulated output at exactly 13.8 volts, which is great. The actual pack, it's not cheap. If you're buying the cells, they're very expensive. They're about $5 each. So that's more than half the cost if you're building this purchasing everything. I managed to salvage these cells, so that means that you can save yourself quite a bit of money, but it really depends on what you want to do with it as well. So I added the extra battery monitor, bought a charger as well, a good BMS, a good well-designed system that's going to be relatively safe, and it looks like this, right? So you can see it's not the most tightly packed, and we could potentially fit more cells into this box. But it gives you an idea. This whole box weighs about 16 pounds, so 26 amp hours and 16 pounds. It's not bad. It's not great. The fully assembled weight with everything in the nice box with all the switches, you lose out on a lot. You lose out on a lot of the energy density gains that you would have gotten by having a lithium battery. So just something to think about. With the buck converters, the two things ham radio operators always worry about, one is efficiency and the other is HF noise or switching noise. I haven't characterized the switching noise on this particular regulator, but you can spend more money and get a better one, so that's definitely an option. And from an efficiency perspective, they're actually not bad. This is a 30 amp buck converter, and at 1 amp output current, it's got an 87% efficiency, so that's about as low as it would go. At 22 amp output, so 70% of its rated capacity, you're at about 96% efficient. So it's actually surprisingly efficient when you're at the at or near the rated capacity. And this is important to note because we were talking about the trade-offs of using a buck converter or a boost converter versus just not charging a battery full if you're using a 4S lithium pack. And if your delta here is only 5 or 10%, that's kind of in the noise. So not having a buck converter there could actually be a very useful solution. You just have to make sure you never overcharge that pack and accidentally plug into a radio that can't handle that voltage. So that's just something to keep in mind. And then I love showing this graph. This is using the West Mountain Radio CBA, or Computerized Battery Analyzer discharge system. So this is a 5 amp discharge on this battery pack at the regulated output. So because it's at the regulated output, this is a perfectly flat line at 13.8 volts all the way until it dumps and tanks here at the end, right? And when it tanks, it goes directly to 0 because the low voltage cutout kicked in and then turned off the system. So with a calculated efficiency of about 90% at 5 amps from that previous page at 13.8 volts output, we should be getting around 590 watt hours out of this pack. And sure enough, we got 608, so it's a little bit higher than the rated capacity, which is great. So either the efficiency was a little bit better on the buck converter, or the cells are a little bit above their rated capacity, and that's pretty common when they're relatively new. All right, on to the last section, lithium iron phosphate, sometimes known as Lipo, or LiFePO4, or LFP for lithium ferrophosphate. All the same terms for a different type of lithium ion chemistry. This one came out in around 1996, so about 25 years or so after the lithium ion construction or chemistry was developed. And this different chemistry gives us a different voltage, right? So our nominal voltage instead of 3.6 is now 3.2, and a 4S pack, so 4 of these cells in series, now gives us a really nice voltage range of about 10 to 14.6. When we compare that to our 13.8 plus or minus 15%, that's actually a very good match. So we get pretty excited when we hear about this new chemistry. This is a photo of one of these cells. You'll notice here the part number, it's IFR 26650, so 26650, which sounds oddly familiar to 18650, and it's the same nomenclature, right? So this is a 26 millimeter diameter can and a 65 millimeter long cell. So it's the same length, but they're slightly fatter cells, and it's just different chemistry, but it gives them about 3,000 milliamp hours for that sort of cell size. And that's just something to think of when you're looking at these cells and looking at how to integrate them. When we actually drop this onto that plot, again, you can see these actually sit very nicely with respect to the mobile radio voltage ranges, which is why they're such a good match for amateur radio. This very bottom chunk below that 11.7 volts is less than 5% of the remaining capacity of the pack, and usually you're not going to be going down that far. So really, most of the time they're sitting here in the kind of the mid to low 13 volt range, and that's absolutely ideal for radio operations. So lithium iron phosphate is great from a voltage perspective, matching in. As a result, they're very, very, very available these days as 12-volt battery replacements. You can just buy them for your vehicles just to drop in replacements, and they come fully assembled. Companies like Bioenno Power make these packs with power poles hooked up directly to them so you can plug your radio directly into it. They have their battery management system, also known as a protection circuit module or PCM, directly on board. So this photo on the left, you can see here it's a 4S and 2P battery pack, right? We learned that earlier. And then you have your battery management system sitting on top that does all your cell, your balancing and your over voltage, over temperature, and over current protections, all built into the pack itself. So the great thing about that is these packs are very safe. So they're already built with all the protections. You can't really overcharge them or undercharge them or anything because they'll just protect themselves. And as a result, you can hook them directly up to most mobile radios with no DC to DC converter, and you don't even need an undervoltage lockout or any other protection because the protection's built into the pack itself. And that's a really great thing about these batteries. The other pros and cons, so intrinsically this chemistry is safer than lithium ion, so they don't have as the same kind of thermal runaway concerns. The electrolytes and the chemicals used are generally safer, which means that you don't hear stories of lithium iron phosphate cells going boom as regularly, or anywhere with any sort of frequency. As a result, a lot of people like using them because they just feel safer around them, and they don't have as high of energy density as a result, which is always part of that trade-off, right? So going here to the fourth bullet, like 360 kilojoules per kilogram versus 460 for like the lithium ion. But they do have a higher cycle life. So a lithium iron phosphate, depending on the configuration and how it's used, you can get thousands or even 5 or 10,000 cycles out of them, which is very useful for like solar applications and that sort of thing. So off-grid solar is pretty interested in lithium iron phosphate because you get a much better cycle life, and as a result, they could last, 10, 20, 30 years in service as opposed to, just 1 or 2 years of, or less than 5 years for a lead acid battery. They also have lower self-discharge. It's sitting on a shelf. A lithium iron phosphate battery won't degrade as quickly, and that's really helpful because you can leave them you can charge them up, leave them on the shelf, come back 6 months later, and they've only dropped a couple percent, as opposed to lithium ion, which may have dropped 5, 10, 20, even 30 or 50% depending on how old the cell is and what sort of chemistry. But with any pros and cons, there are always some cons, and the lower energy density and then the cost really is the other one. So lithium iron phosphate is more expensive initially, but like I said, the replacement costs actually have brought it down these days to the point that they're a very economical solution for a lot of radios. So if you can bite the bullet initially, I'd strongly recommend go directly to lithium iron phosphate. Your back will also thank you because they're so much lighter. Okay, so to actually use these, kind of two options, build or buy a pack. You can just buy one from like Bioenno. You can just buy these drop-in replacements. $192 gets you a 20 amp hour lithium iron phosphate battery. If you add a hard case and a charger and some USB ports and power poles, add another $100 and you can make a nice box like this. This one's 10 pounds, fits my 20 amp hour lithium iron phosphate battery really nicely. Some charging ports, USB charging ports. I keep the charger inside there. I always keep the USB cables inside the box as well, really important. And it's just nice to see that. The discharge curve, pretty straightforward. You can see it's a very flat discharge with this drop off at the end, so it looks surprisingly similar to the regulated output. But it's important to note that the voltage isn't very useful, right? It starts at 14.6 or something, or 14.2, but it immediately drops down in the first, couple minutes of use. It immediately drops down to something like 13 volts. In this case, we're measuring at the end of the cable, so it's a little bit lower. But if I told you this battery was at 12.9 volts, what capacity is it at? Well, 12.9 volts is somewhere here in the, I don't know, 30 to 60% range. So it's really hard to judge. So using a Coulomb counter or some sort of inline watt meter can be really helpful just to see how much capacity you've used if you're going on like soda or something. And then the other way you can do it is you can build your own battery pack. So this one was a super fun project that I did. I built my own lithium iron phosphate battery pack, used 50 amp hour prismatic cells from eBay, bought a really nice smart battery management system with a Bluetooth module so I can use it with my phone and program it with my phone and see the capacity and everything. Powerworks was nice enough to give me a mega box, this bright orange box with a whole bunch of USB ports and extra power poles and flashy lights on it. Really, really fun box, and it's bright orange, so I'm a fan. And it actually comes out pretty well. So looking at the whole box all together, it's about $506 worth of parts, compared to the equivalent Bioenno battery by itself is about $470. If you look at just the battery itself, you can see building your own battery can be very cost effective these days, but you have to know what you're doing, right? There's a lot of energy at these terminals. If you accidentally drop a wrench across that, your house insurance will not be happy. So definitely be careful if you're going to be building your own packs. This is what it looked like complete. Again, I keep pouches, insulated pouches with cables, all the extra chargers and cables and USB cables in there, all the ports on the top, and the nice box inside. It's about 19 pounds for this box. Very nice. Love the bright orange color and just bring it around anywhere. A couple quick shots of the app that you can use. The app lets you configure all the settings in the battery management system, so that's really useful. And it's just a nice kind of way to read up. The battery nerd inside me loves this. I can look and see, oh, my battery's at 68%. I'm currently pulling 10.5 amps. This is the battery's temperature. I can get the individual cell voltages of each cell. And if I ever need to tweak any of the settings or change any of the current or voltage thresholds, it's really easy to do with the app. So I really enjoy this. It's been a super fun project to play with. Strongly recommend. I've got all the links in the back of the presentation that you can view. So yeah, here, same thing, do the same discharge test with the CBA4. You can see the voltage again, very, very flat all the way to the end. And at this very end, when you drop below 11.7 volts, it's just that last like couple percent. So really, from an amateur radio usage perspective, these are absolutely ideal. No complaints. I also added this little USB-C PD power delivery module, so I can get 60 watts power delivery and charge laptops straight from this pack. So that's been really fun to play with. DC to DC modules are really fun. All right, so to finish it out, kind of a quick comparison table. I just threw this together with some colors just based on my thoughts. Lead acid, very available, very cheap, pretty straightforward to integrate, relatively safe but really heavy, and they don't like discharge and their energy density is terrible. Lithium ion, not bad, but pretty like it's more dangerous and it has higher you know, integration concerns and protection concerns. Lithium iron phosphate is really a great fit. It is the highest initial cost per amp hour, but your long-term cost is well managed by having one of these packs. They don't weigh as much. They are really easy to integrate with amateur radio because they just work. It's the right voltage and it just plays happily. So if that's a selling point to go get yourself a lithium iron pack, lithium iron phosphate pack, or build yourself one, hopefully you do so safely. Lots of links at the end of the presentation here that including a number of YouTube channels that have some really good information. So strongly recommend that. But that's all I have for you today. Thank you very much for attending this talk. I've got a couple other presentations this weekend as well, and a special thanks to Eric and the team, Brad, Emanuela, George, and Rachel for all their work putting on this once-in-a-lifetime event. It's really cool to be able to participate and to play back. So looking forward to the Q&A after the presentation. Thank you.